AI deconvolution. Is it even possible? All right, let's have an honest conversation about AI, deconvolution, and sharpening. Can so-called AI deconvolution tools hallucinate? Do you even have AI deconvolution tools in astrophotography? Welcome to Deep Sky Detail. So why am I making this video? Well, I'm in the process of updating AstroSharp, which is my free astro sharpening tool, and I'd like to talk about some things. Side note, if you'd like to support the cause of free AI astrophotography tools, consider supporting me as a channel member or as a member at buymeacoffee.com. So back to why I'm making this video. Another reason is Lutza from the Space Koala just uploaded a great video on the topic too, and there are some things that I'd like to add to the conversation. I thought I'd make a quick video and add my 2 cents. I'll be mainly addressing 3 points. First, I'd like to talk about so-called generative models versus other types of models. Second, I'd like to have a discussion with you about whether AI deconvolution is even possible, and whether we would even know if it happens. And third, I'd like to discuss whether AI deconvolution tools can hallucinate. I hope to give you my thoughts and to learn yours, and maybe turn this into sort of a mini series of videos to discuss the larger issue of image processing and AI. But first, we need to establish some things. Let's get into deconvolution at a very high level. I'm going to speed this up because some of you may find it a bit dry, and I plan on doing a more in-depth video later on. Let's define some things. Let's say you have an out of focus or blurry image I. I is going to equal some original image, O, that is convolved with a point spread function, plus some noise. Convolution is sort of a mathematical operation, and it is used to model how the original image gets blurred. The blur, which is represented by the point spread function or PSF, can happen with diffraction, atmosphere, guiding errors, etc. You take the brightness values of the point spread function and multiply and add them to each pixel in the original unblurred image in order to blur it. This convolution makes the image look blurry. So deconvolution aims to remove the point spread function's effect from the image. This means that there is a lot of dividing and subtraction going on, and it's tedious. So a lot of times a Fourier transform is applied to the PSF and image to make the math easier. What makes deconvolution much harder than convolution is that you have to know what the point spread function looks like for your setup, and you have random noise in the image that is unrelated to the original convolution. This noise wreaks absolute havoc on the division during the deconvolution process, making true deconvolution practically impossible. So the main takeaway is that convolution is much easier than deconvolution. Just like making a cake is a lot easier than figuring out after you've baked it what the ingredients are. There are some very smart algorithms out there that help mitigate the noise's effect on the image. This allows for a good estimate of what the deconvolved image should look like. So as you know, a couple years ago, I developed AstroSharp. AstroSharp is an AI sharpening tool. It currently works by taking 1 pixel at a time and increasing or decreasing its brightness based on the values of the surrounding pixels. It is not fancy, but it kind of works better than I expected for sharpening astrophotography images. I trained it by using several different point spread functions on sharp images and then tried to have the AI reverse the blurring. Now, some of you might say, well, it was trained on images blurred by a point spread function, and the neural network tries to remove those effects. So why not call it a deconvolution tool? And that's where we need to talk about AI kind of in general. AI nowadays, to me, just means neural networks. A neural network takes some input, transforms it to numbers, and through a series of functions converts the input into an output of numbers. Those output numbers can then get reinterpreted as something else, like another image, language, or whatever. This can happen in one step or in several. There are different types of architectures, like simple feed-forward models, convolutional neural networks, etc. Lusa from Space Koala did an excellent video on this recently where she brought up a ton of good points about AI. She describes the basics of AI really well. I'll leave a link in the video description of her video. So she described so-called generative models and discriminative models. She described discriminative models as models that enhance or classify data, while generative models generate new data based on what it was trained on. I agree with mostly everything she said. In her video, I'd like to add some caveats though about generative and discriminative models kind of in general. Why would these two types of models matter for us in astrophotography? Well, a purely generative model would be producing mostly new data that wasn't part of your original image or stack of images. If we're using generative models, then I think this opens up a can of worms regarding the integrity of the hobby. Are we really imaging space, or are we producing AI art? To me, the distinction between discriminative and generative is not exactly so cut and dry. A purely discriminative model discriminates between different options. Text recognition is a great example of this. Based on some handwritten input converted to pixels, such a model would give an output that is the model's best guess for what letter or number is written. It discriminates among different options. A purely generative model, in theory, could take some input and generate a novel output. There are some AI models that take random pixel values and turn that into an image. There is no underlying real image that it is trying to recreate. There are some AI models that take text prompts to create an image. Somehow, in the process of its training, it has mapped characteristics of the input into the output image. There are some generative models that take colored shapes and turn them into pictures of streets and buildings, and the shapes usually make an outline of what they should depict. These models that take shapes and turn them into buildings are called image-to-image neural networks, or pix-to-pix models. Neural networks feel a little bit like magic, and I think in part it's because we don't fully understand them. So instead of dichotomizing neural networks into discriminative and generative models, let's make a continuum. On one side are purely discriminative models. These are things like text classifiers. On the other side are generative models. Models like Stable Diffusion or chatgpt. And instead of saying discriminative or generative, let's define this dimension as how restrictive the output is. So we'll call this restriction. For a text classifier, the output is very restrictive. It gives probabilities of a number or letter being a letter or number. For example, what's the probability of this being a 7? For chatgpt, the output is not restricted. So we have similar prompts can give you multiple novel outputs. Keep in mind that the novelness of the output is usually unrelated to the size of the output. ChatGPT's output is less than one word usually. So if we take the word like unbelievable, un is an output, believe is an output, and able is the next output. All of these small predictions add up usually to a coherent response. Just because the output is small doesn't necessarily determine whether it can make mistakes, because ChatGPT can make a lot of mistakes. So where would a image-to-image translation model be on this continuum? Like a model that turns outlines into pictures. This type of model should be fairly constrained. Like an outline of a person should make the neural network put in an image of a person. But there is substantially more freedom in the output than there is in the text classifier. The output image of a person could be blonde, brunette, have green hair, have brown eyes or blue eyes or whatever. The model is creating something that wasn't there before, so it probably belongs somewhere in the middle. And now is the big question for us astrophotographers. Where is a tool like AstroSharp or BlurXterminator on this continuum? I can't say for sure, but these models are doing a lot more than just discriminating among different options. To me, they feel like they're taking an image and improving it, but keeping most of the data intact. Just one small warning though, all the publicly available astro-enhancing tools that I've seen, whether it be star removal or so-called AI deconvolution tools, more on that in a bit, have model architecture that is similar to image-to-image translation models. So that leads to an even bigger question. Is true AI deconvolution even possible? Let's finally try to put AstroSharp and other Astro tools on this line. They are using an input image and producing an output image that is more detailed than the original image. Where does the detail come from? Deconvolution? For something like BlurXterminator, the answer is, I don't know. The code is proprietary. I have some guesses, as to how things might work. First, I don't know how the model was set up. Maybe it really is dividing a Fourier transformed image by the Fourier transformed PSF and then only using the AI model to estimate the noise in an intelligent way to remove artifacts. I've tried it this way, but haven't yet been able to make it work. But maybe BlurXterminator was set up that way and training went exactly as intended for that to happen. If that is the case, that would be a lot like traditional deconvolutional techniques, like the Wiener filter, for example. I would be much more comfortable saying that something like BlurX is mimicking something akin to deconvolution, but I don't know. What about AstroSharp, or the new version of AstroSharp that I'm working on? I'm in the process of creating it, and the answer again is I don't know, but probably not. And I have access to the code. The problem with training neural networks is you can set the inputs, you can set the outputs, you can create the network to attempt to mimic the steps in deconvolution, but the neural network is going to find that solution that makes the output look like you are telling it what it should look like. There are so many variables in a neural network that it could find countless ways to make the output look believable. But that does not mean it is doing deconvolution. But I think the bigger question is this: is true deconvolution even possible? Astrophotographers and astronomers developing AI deconvolution tools in the first place, why don't they just use non-AI tools like the Wiener filter or Richards-Lucy deconvolution? Those are already available, and you can find them in Serial, for example. I already told you in the beginning of the video, you may have skipped it, but hopefully you didn't, but let's do a flashback. And you have random noise in the image that is unrelated to the original convolution. This noise wreaks absolute havoc on the division during the deconvolution process, making true deconvolution practically impossible. So perfect deconvolution is, for all intents and purposes, practically impossible. Non-AI techniques like the Wiener filter and Richardson-Lucy deconvolution are only estimates of the real deconvolved image, and they fall short when star shapes are really irregular. AI is being used to get better results. But are these tools performing deconvolution similarly to the non-AI techniques? I don't know, but let me ask you this. Consider an AI that removes the stars and the high-frequency noise of an astrophoto, sharpens the deep sky object, then replaces the stars with perfectly round stars that are proportional to the ones removed, and then adds back in the high-frequency noise. Is that deconvolution? I don't think so, but it would produce very similar results to an AI tool that did near-perfect deconvolution. Both models likely have millions of parameters. To figure out what is really happening with each model would require examining interactions between millions of parameters, and that would just take a very long time. And that leads me to two questions that I don't have the answer to. Would we even know if an AI is actually doing deconvolution? And if one neural network's results are indistinguishable from deconvolution, does it matter if it really isn't mathematically approximating deconvolution? Feel free to comment what your thoughts are. So I don't really like the term hallucinate with respect to artificial intelligence tools. I don't know what it means. Humans hallucinate, machines don't. But if we put the question in better terms, can AI astro enhancing tools like AstroSharp and BlurXterminator add detail that isn't there? And I think the answer is probably yes. With AstroSharp, I'm pretty sure that it does. How do I know this? Well, because deconvolution algorithms that don't use AI can create artifacts that aren't really there, especially in the noisy parts of your image. For example, deconvolution can take several noisy pixels and clump them together that makes it look like nebulosity or a small star. And these algorithms have far fewer parameters than AI algorithms. Even if the probability of a group of parameters creating an artifact or adding detail is small in an AI tool, there are so many parameters that at some point these neural networks will most likely produce fake detail. Now, you may say that AI enhancing tools are only looking at small regions of an image at once, and this should reduce the number of artifacts and our fake detail. But let's go back to ChatGPT again for a second. ChatGPT predicts less than one word at a time. This is called a token. To me, that's similar to fixing one pixel at a time in an astrophotography image. Of course, ChatGPT can use previous context to predict each token, so the comparison isn't quite the same. BlurXterminator, to my knowledge, isn't going to use a patch of sky in the corner of an image to predict what is in the middle of the image. So there's protection from it faking large-scale detail or structure. The same is true of AstroSharp. Let me show you an example of how detail can be sort of interpreted at a smaller level. Here is a zoomed-in image of the Veil Nebula I took a few years ago, and here's how AstroSharp sharpened the image. There is some extra added noise compared to the original version, but let's focus on the wispy nebulosity here. It seems like the version of AstroSharp is doing a decent job at sharpening the image. To me, it looks sharper, and there isn't anything other than sort of the extra noise that doesn't make sense. It doesn't seem like there's any funny business going on. But let's now go back to the original image. I'm going to show you the same image, but processed with a newer image of AstroSharp that I've been working on. Again, in this newer version, the image looks sharper. Nothing looks out of place. It doesn't look like it invented any detail. The wispy nebulosity here seems reasonably sharpened. But now, let's compare the previous version to the newer version. And there are differences. They're both reasonable interpretations of the original data, in my opinion, but they're different even though both models were trained on similar data. The newer model is making different assumptions about how the original image was blurred. So which one is more true to what the Veil Nebula actually looks like? I don't know. And that might be a problem. Don't get me wrong. Traditional deconvolution algorithms also struggle with similar issues. Deconvolution is not a truly solved problem. Different deconvolution algorithms also produce different results. Just because people are using AI to try to mimic deconvolution techniques doesn't mean that those issues are going away. So to sum it up, I'd like to give you my opinion of what we've talked about so far. Keep in mind, these are just my opinions. Yours might be different, and that's okay. And my opinions might change based on what you tell me. First, are image-enhancing AI tools more generative or more restrictive in nature? So let's go back to this continuum here. I think that image-enhancing tools are very similar to image-to-image translation tools, which are generative, at least in how the models are set up and created. But I do think they are more restrictive than pure image-to-image translation tools. So I would put them somewhere closer to the restrictive side of the continuum. So they're not fully generative, but they are quite restricted in what they can output. So second, can image-enhancing tools hallucinate? First, I wouldn't call it hallucinating. I would say that these tools can create artifacts or detail that isn't there, especially on smaller scales. Third, do we have AI deconvolution tools yet in astrophotography? The answer to this, in my opinion, is I don't think so. Don't get me wrong, I think a lot of these tools are really great, and a lot of care has been taken to make sure they enhance images in reasonable and good ways. And maybe BlurX is really doing deconvolution under the hood, but I don't have access to how the model was trained or the architecture of the model. I only have information about what Russell Croman has said publicly. He is confident enough to say that the tool is doing something similar to deconvolution, and he markets his product as AI-assisted deconvolution. I personally have not seen the proof of that. I haven't seen it in AI models that I've created or in other publicly available models. But having said that, I also have seen very smart researchers in a paper base their model on the steps traditionally involved in deconvolution. They have a neural network that estimates the PSF, then they have a separate network that processes the original image, then they take the outputs of both networks and input them into a Wiener filter. A Wiener filter is one traditional way of estimating a deconvolved image. So the neural network should theoretically be figuring out what the PSF is, and how to deal with the noise in the image, and that would be very close to an AI-assisted deconvolution tool. But with neural networks, what happens in theory and in practice might be totally different things. There are just too many parameters to know for sure what is going on under the hood. And finally, will I be using AI enhancing tools for my images? Yes, I already do. I still think they're useful. They're not perfect, but neither are non-AI enhancing tools. The questions I think I'm asking myself are this: are the tools changing my data unreasonably? If the answer is yes, then I wouldn't be using it. For example, is an AI tool creating large-scale structure in my image that was never there? If yes, then I shouldn't use it. However, if the tool is sharpening my data in a way that is faithful to the original data, then that seems reasonable. I will use the tool in that case. Maybe you have a different opinion. Maybe you can convince me otherwise. Let me know in the comments. And if you enjoyed this video, please subscribe if you haven't subscribed. Leave a like too. That would be a nice thing to do. Thanks for watching.